Okay, so let's continue. We are working on equilibrium of rigid bodies. That's what we are working right now. So I'm kind of preparing all that we have been doing, learning how to calculate the moment, learning how to replace distributed loads by concentrated loads. And also what we did for equilibrium of particles is gonna be tools that are gonna help us to find or to analyze equilibrium of rigid bodies. That's what we are working now. That's what we are doing now. We are working this equilibrium just in the plane, in 2D. So it's like if you have this, let's say this is a body here, a general body here that is on the XY plane. If we are analyzing the equilibrium of this body, means that the body should not move, or if it's moving, it's just a constant speed, no acceleration, in the x direction. So it shall not move in this direction, it shall not move in the y direction. So and now that is a rigid body, it cannot either rotate, it cannot rotate. When we analyze particles, we only analyze horizontal motion, vertical motion. If you analyze horizontal and vertical, you are considering like any motion, because any motion can be decomposed into x motion and y motion. So if you don't have any motion in the x direction and you don't have any motion in the y direction, you are not doing any translation. And for particles, that's enough for equilibrium. But if we have a rigid body, we have to consider also rotation. This should not rotate. It should not rotate. So not only we cannot have translation in the x direction, we shouldn't have translation in the y direction, and we should not have rotation. If we guarantee those three, we can say the body is in equilibrium. So we have acceleration in the x direction equal to 0, acceleration in the y direction equal to 0, and rotational acceleration equal to 0. Let's say around any axis perpendicular to the screen. So, and this comes from F equals mass times acceleration, right? So if this is 0, then it's because this force is 0, or in this case, if this acceleration is 0, it's because the moment is 0, right? Because this value, m is never 0 and I is never 0. So for the condition of acceleration 0, you have to have forces 0 or torque or moment 0. And the forces, we say, in the x direction and in the y direction. So with the summation of forces have to be 0. Summation of forces in the x direction has to be 0. Summation of forces in the y direction has to be 0. And summation of moments about, let's put an axis O, meaning an axis in this direction, right? So it shall not rotate on the plane. If you guarantee these three conditions, we can guarantee equilibrium on the plane. Equilibrium. So those are three conditions that we can use to guarantee the equilibrium or to solve the unknowns that we will have in a particular problem. Eventually we will have a body with some forces that are acting on the body in any direction. All those forces you can decompose in x and y components. So you can decompose this into x and y, this into x and y. This is also only x. This is a little y, a little x, a little. Let's say this is only y. So you get all the components in the x direction, you get all that summation of all those components, and you set this summation equal to 0, and you solve for your unknowns. Same thing for y. And then you choose any point, and you calculate the moments around that point, and you set that equation equal to 0 in order to create the conditions for equilibrium. In any specific problems, well, you don't know all the forces. You know some loads that apply or some forces apply on the body, and you have to find the reactions on the supports. So this equation will give you the forces that are required to be acting on the supports for the body to be in equilibrium. That's the general idea about equilibrium in 2D for rigid bodies. Very similar to particles. To particles, we only analyzed this portion here, and we were able to find two unknowns. Now we add the rotational ingredient here, so we are able to find another unknown. So in general concept, is there any question? It's kind of similar to particles with one more ingredient, rotation. And you know how to calculate moments already, right? We spent the past few classes studying how to calculate moments. And eventually you might have a distributed load here, because now we have dimensions, so we can put a load like this. So we need to replace that load in order to do the calculation of the equilibrium, the analysis of the equilibrium of that. We are going to replace that by an equivalent load here. So we can do summation of forces and summation of moments with respect to any point that you choose, and do your calculations and your equations. So that's why we learn how to replace this kind of loading for this. So problems that we are going to solve will be something like, for example, this very simple problem. This little problem is a problem that we need to solve. We have a beam that is has this weird support here, like a tube with a collar here and a little pin here. So under this load, what are the reactions here and here? That's what we as engineers have to find out. Once we find the reactions here and here, then we can give this to the designer so it can design the support so the beam can hold that load. Problems like this. I have a beam with some distributed loads, some load here, some moment applied here. What are the forces here at the wall? This is a cantilever. So in order for this to hold all this loading here, you have to design this support really strong enough to hold it, right? So we need to find what are the forces that this support has to endure, right? That's what we're going to learn how to find. Some more examples. Simple example here. Another beam, we need to calculate what is the force here at the support and what is the tension on this cable. So we guarantee that this beam stays there and doesn't fall when they bring a load of 500 newtons and put it here. So we need to be able to guarantee that this doesn't fall. More examples. They give us some information about these loads, and we need to find what are the forces here, so we can design the foundation here. Right. More examples. Maybe some of these are in your homework. Another example here. Find the tension on the cable and the force here at the support. Here, find how much force this guy has to apply here in order to lift this up. What is the force on the wheel? Find the forces at the support. Find what are the reactions here at the points of contact of this, if someone applies this force here. Those are the kind of problems that we are going to analyze. So one more thing that we need to learn before we actually start doing these problems is, as we did with particles, we need to do a free body diagram. Free body diagram, we isolate the structure and we put forces on the structure, and then we do the equations of the forces. So, like here we see some forces. Here we see some forces. But we don't have forces here, and this is what we need to find, the forces here. and the force here. So we need to replace this by a force, and we need to replace this by some forces. Same thing here. We need to replace this wall because we cannot put a wall on an equation, right? We need to put forces in the equation. So we need to replace this wall by a force or one or two or three forces here. We need to replace this by forces. We need to replace this by forces so we can analyze the equilibrium and put those forces in the equations. Well, that's what we have to do in order to set up the free body diagram, replace the floor here by some forces. Same thing here, the supports, we need to replace by forces, we need to replace this by force. We already know how to replace this cable by forces, right? And we know that these forces are equal here because this is a pulley, so in this one we are almost done. But how about this? What forces do we put in here? Okay, so that's the next chapter. Now we're gonna see how you will find different kind of supports and how you replace the support by the required forces or the equivalent forces. So those are here in a table that you can find in any textbook. Different types of support that you might encounter. So you should, if you see these tables are not exactly the same as what I showed you in the previous examples, but you can assimilate those examples that I showed you to any of these, either this or this, or this, or this, or this, right? So first there are these kind of supports where you have rollers like this or like this. You replace this by just one force because this kind of support can only apply one force. And the way I do this is try to imagine, and we always decompose these things either in X and Y or in rectangular components. In general, X and Y, but sometimes you have like an inclined plane, so it's better to do rectangular components in the direction perpendicular and parallel to the plane. But let's say in general, rectangular components. So, like in this case, you think yourself, if I try to move, this is kind of like the leg of a structure. If I try to move this leg horizontally, can this move? If I push this to the left or to the right with this kind of support, with this move, it's gonna move because just those rollers there or this. If you push this, it's gonna move, right? But if you try to push this down or up, can this move this up or down? No. No, because there is like a wall here or a rail, right? Or here on the floor, you cannot move it down because the floor is not letting you to go down, right?
As long as the floor is level.
So, what?
As long as the floor is level.
Level?
The floor is flat, I guess, perpendicular.
Yeah, the floor is flat. So if you try to push this leg down, it's not gonna go down because the floor doesn't allow you, unless the floor fails, right? Well, the idea is that we engineers build this floor in such a way that doesn't fail, so the structure stay in equilibrium, right? So if you try to push this down, this is not going to allow this thing to go down. It's going to apply a force to avoid that motion. So that's how you know that in these cases, only one force is going to be necessary to replace this in a free body diagram by just one force. You don't put force horizontally because this can move freely. See, this one also, if this is a frictionless surface, it's going to move freely to the sides because there is no friction. So there is no force here horizontally, right? Let me move quickly just to this one to see the comparison because all of these are similar. This one. If you try to move this horizontally, can you move it? This, no. You cannot move it because it's fixed, right? And there is a pin here that doesn't allow horizontal motion. It means that this support will create a reaction that doesn't allow the horizontal motion. So this force is exerted by the support on the structure to avoid horizontal motion. And you cannot move this vertical either, right? Because of the same thing. So that's that's why you know that these four exist. These four exist. Actually, what is happening here is there will be a force in some direction that we don't know, more like this, and we don't know the angle. We don't know the angle. So we can consider this unknown, this as a force at at a direction that I don't know. So I have the magnitude of the force and the angle. Those are the unknowns. But this is very ugly to operate on equations. You start to deal with sine and cosine of an angle that you don't know, and it just becomes ugly. So you better forget about this, and you get the components of this, this component, and this is just a number. This is just a number that you need to find. And once you find this number, you just do arctangent, and you get the angle. In case you want the angle here, you just get the arctangent to get the angle, and you do Pythagorean theorem to add these two forces and get this value. If you want what is the actual value of the reaction and the actual direction. If you are happy just with working with the components and your answer can be accepted in rectangular components, well, you just leave these numbers as your final answer, okay? So you replace this kind of support by these two forces. You could do this also, but I don't recommend. Nobody recommends. Nobody does this. Only people that like to learn and know a lot of trigonometry and knows all the qualities in trigonometry stuff, and they're very good at that kind of math. They work this just to show off, right? We will do like this. We are lazy for algebra, right? And this one, same analysis here. Can you move this horizontally?
No.
No, so there will be a force here. You cannot move this vertical because it's stuck on the ground. So you cannot move this up and down, so this force will be there. And you cannot rotate this because it's like anchored there, right? So you cannot rotate it. This doesn't allow rotation. So there's gonna be a moment here on the ground avoiding the rotation of this leg here. So this kind of support you replace by these three unknowns, and your work of the analysis of the equilibrium will be to find these forces that guarantee that this thing doesn't move in any direction. Right? The others that I skip, like this cable, you can consider this cable as a support that is holding this leg of, there is some structure here. So you have this cable. Well, this cable will apply some tension in that direction. And you know the direction because the direction of the force is the same direction of the cable. Right? And same for this short link. There will be a force in the direction of the link. This link, apply a force here in the direction of the link, like it's showing here. This is another case of a force, one force of known direction. In all these cases, you should know the geometry of your structure, so you will know the angle of this force. The direction is known. You just need to find the magnitude. Same thing in this case. You see, this is like a frictionless rod with a collar here. If you try to push this collar in this direction, in the direction of the rod, you can move it, right? Because it's frictionless. But if you try to move this in this direction, there is no way you can move this because there will be a force that doesn't allow you to move in this direction. So this force is going to be applied by this rod on the collar, which is applied on the structure here to avoid the motion perpendicular to the rod. Same thing here, right? This can move in this direction, but cannot move in this direction. Right? We already talked about this. Okay, so So let's put this in practice. Where were we?
Do you have that table on Canvas?
That table is in Canvas.
Yeah.
Yes. And you find it there. But in any textbook, or if you put in Google, support. Well, to put something like that, support for equilibrium of rigid bodies, you will find it. Support. So we are going to do a free body diagram now that we know we have all this knowledge. So how do we do that? I'm gonna put here the steps that you need in order to draw a really good free body diagram. You should have this, you should know this by heart. And the next exam I'm going to ask you what is the 17th word of the third step. Right. Yes. I should, right? This is actually too many words, as you don't need to know those words, but you need to know what they are. And we did this already with the particles, right? I just put it here just to make it very to make a big emphasis on the free body diagram, because we have been doing it with particles with relative success. We have to keep using it for free body diagram, for rigid bodies, and you will have to keep using it forever in your practice. So you have to be very good at this. And you will recognize that we did this in particles. Look, first step, select your system. So if you need to find in this problem, find the reactions at point A and B. So you need to find the forces here and the forces here. So you need to select your system in such a way that the forces here and the forces here show up in your diagram, right? So for those forces to show up, you need to remove whatever is applying those forces. So you're going to remove this bar, and you're going to remove this support. So you're going to see a force here, and you're going to see some forces here. So you have to choose your diagram in order to show the forces that you need to find. So I select here the beam. The beam will be my free body diagram. So I will do something like this. That will be the free body diagram, right? You can select any part of the structure that you need in order to see the forces that you have and that you need to find. So let's see. Draw your, now that you selected, you draw it, right? Yeah, that's the drawing of the completely isolated body, the free body. Draw the forces and moments, not only forces, but moments that every element erased exerts on your system. So in order to have this, basically what I did was erase this stuff, right? So the forces of the elements that I erased should show up here to represent the elements that are gone. So this kind of support, we saw it on the table before, right? Is this kind of support, right? Is this kind of support? No, it's not that kind of support. Oh, we don't have that one here. Ha, of course, I choose the one that it does bad. But let's analyze that one based on what we said. Where were we? Oh, that table. This is a really nice support. That table doesn't have it. I didn't know that table doesn't have it. Does it?
Come on.
I don't.
Pins.
Which one?
Go down. Fourth one.
Here? Here? No, I don't see it, because it's the same as this one, but without the pin. See, this has a pin. This pin allows rotation here, right? I can rotate this and no problem, right? The other one is this fixed. I'm gonna put into this table that and send it to Himmler. What?
If it's fixed, it has 3 unknowns, right?
Let's check. That's a good challenge because we need to develop our own item for this table that is not included. Let's analyze what's happening. Here. Okay, so let's analyze that. Can we move this? Can we move this horizontally? If I try to move this horizontally, can I move it?
No.
No, so there must be a force horizontal here, right? Let's put it. Horizontal force, okay, horizontal force. Oh, in which direction shall I put that force? It doesn't matter. This is an unknown. We don't know this force. So since it's an unknown, well, I don't know if it's going to the right or to the left. So once you put the force, put it any direction you want. That when you find the solution, if the direction was correct, the solution will be positive. And the direction was wrong, the solution will be with a negative sign, telling you that it was in the other direction. So don't worry about that. But let's continue with our finding the replacement for this support. Can you move this up and down?
No.
You cannot move it up and down? Yes, you can.
Are you
Right, because this is a color on a frictionless rod, so this can move up and down. Nothing avoids the motion, right? Don't look at this, right? It's not gonna move up and down because probably this doesn't let you go down. But we are talking about just this support. Imagine the support just by itself. Imagine the support just by itself. Just by itself. Can you move this? Can you move this up and down?
Yeah.
Yes. It's like a color here, and it slide down or up. If I push up or I let it go down, nothing will avoid this motion, right? This can move down, but I cannot move it horizontally because the rod is fixed and doesn't let me move, right? See, this rod is attached here, so this is not gonna move horizontally. So if I try to move this horizontally, it's not gonna be able to move because this bar is applying force to avoid the horizontal motion. That's why we put this force here. Is that clear for everybody? You have to analyze the support just by itself. Forget about the rest of the structure because this is not gonna move. This is not gonna move up and down because it's in equilibrium. No, because this kind of support is not allowing the motion in the vertical direction, but probably because this interact with this and at the end this doesn't move up and down, but not because this support applies force vertically. See, there is no vertical force there. You see it? Now can you rotate this like this? Can you rotate it? This cannot rotate because of this configuration, right? In order for this to rotate, you have to bend the bar, right? If you rotate this, you bend the bar and you break the structure, right? Is it clear? So there is a moment here that opposes to the rotation. So I put this force, this moment here, indicating that if this beam tries to rotate like this, there will be a moment not allowing that rotation. If I try to do this moment will avoid that motion. If I try to move it up, this force will try to, so we don't know the direction of this. It will depend on the tendency of these two rotating in one direction or the other. That will be, the equations are gonna tell us that. At the beginning you don't know, so you just put any direction, and if the result gives you negative answer, means that this is in the other direction. Okay? So this kind of support will be replaced by these two forces. Well, actually a moment and a force. We say forces in general. So that kind of support has to be replaced by this kind of, so we should add it here, right? We should add it here. This is instead of putting this, we should put like this kind of, right? Ugly. Ah, so now we now have our own more complete table. Okay, is that understood for everybody? So you can use the table for the cases that you have. If you don't have a case, well, you just think about it. To check, okay, this support allow me motion in the horizontal direction. If yes, then you don't need a force. If doesn't allow you horizontal motion, then there is a force that avoids the motion in horizontal. Then the vertical, and then the rotation. Those are the three conditions of equilibrium: horizontal motion, vertical motion, and rotation. Let's continue with the analysis here. So we replace the support A by the forces. It says here, draw the forces and moments that every element exert on. Okay, we did that for this. How about this one? What force will be applied here? Can this move horizontally?
Yes.
Yes, so there is no horizontal force. Can this move vertically?
No.
No, there will be a force that is going to avoid the vertical motion, so you have to put a force right here, right? So this is replaced by this. What else? Look, the force do not include internal forces. Well, we don't have much of an idea about what is an internal force, but maybe in another example I talk about this better. The forces that we are drawing in this step, what it says here is that these elements that we erase usually apply these forces at the point of contact. So where this rod touches this color here, that's where these forces apply. So this force is like in this little thing here, that's where the forces are applied. Where this little roller is touching the beam is where the force is applied. See, the force is applied right here. That gives you a hint where to draw the forces. Wherever the element that you erase in order to leave this free, at the point of contact where you remove that element, that's where the force is applied. That's what this means. Forces act at the point where the erased element touches your system, except for gravity and magnetic forces, things like that. We are not considering the weight of this beam. But if you consider the weight of this beam, there will be a force here in the middle for the weight, right? And there is no contact. The earth is here, and the earth is not touching the beam right there. But that's where you put the weight, right? At the center of gravity, not necessarily at the point of contact of the earth, which is the one that is applying the gravity force on the element. Okay, what else? If a force is unknown, it is usually more convenient to draw its rectangular components. We don't have that case here. That was mentioned when I was talking about this kind of support. It's better to put the components instead of the force and the angle. But that's what we are doing when we talk about, okay, can this move horizontally? Okay, so let's put that force. Can we move vertically? Okay, let's put this force. Or you can think of, well, there will be a force here in a direction that I don't know, so it's going to be something like this. But it's ugly to work this way, so you better work with the components of that force. And you have here two unknowns. If you do it like this, you also have two unknowns, 1 and 2. What else? What else? What happened? If a force is unknown, it's usually more common. Unknown forces, assume as in the wrong sense, will have a negative sign when found. I mentioned that already. Okay, so don't worry about in what direction to draw those forces. Put anything. Just don't waste time thinking in what will be the direction. Just put it anyway, and you will get a negative sign if you put it in the wrong direction. Now, label each force. Well, I have to draw all the forces, so I have to draw also these, right? The loading that is applied on the system, well, you have to draw it. So you draw your load. Ugly. So you draw your force here. And then label each force by its magnitude if known, or by a convenient symbol if unknown. So the one that we know, we put the value. So you put 200 here. And the one that you don't know, you put a label. So I will call this one like reaction at A, or A sub X, or any convenient, a name that has something to do with what it really is. So I could call this maybe AX, and this one moment at A, and this one reaction at B. Or I could call it B sub Y. You put any name that has something to do with the labels and the elements of your structure. And sometimes it's convenient to put the dimensions. If you don't have the other diagram close to that one, it's very good to put the dimensions, but it helps a lot to have those dimensions just right there in the free body diagram, and then free body diagram. That's your free body diagram. Okay? Very important, the fifth point, the free body diagram must be done very neatly and must be of a convenient size so all its elements can be accommodated clearly. Okay? This is not new. I've been talking about this when we talk on the particles, but it's a good idea to have it right there. You have it in your canvas. Now that you have your free body diagram, what is next? Setting up the equations of equilibrium in order to solve for the unknowns. Here we have the unknowns 1, 2, and 3. We have 3 equations of equilibrium, so we should be able to solve this problem. Let's set up those equations. First equation, summation of forces in the x direction has to be equal to 0. That's the first equation of equilibrium. And you set up a sign convention for each equation. You can put negative to the left, whatever you want. It's just for that equation. Here I'm going to put positive to the right. I assume it's convenient for this case. So what forces do we have in the x direction? Actually, only AX. So AX. Do you see any other force in the x direction here? No more forces, right? It's kind of like an too easy problem. So once you put the summation, you put all the forces that you find, then you do equals to 0. You write equal to 0. So from here we found that AX is equal to 0. Just so easy from that equation. Well, this is just an example to show the procedure. So we don't want to get confused by a complicated problem. This is just to get the concept. Second equation, summation of forces in the y direction equal to 0. I'm going to put positive going up. What forces do we have in the y direction? Well, we have this in the y direction, right? This is vertical, and this one, right? But we cannot put this in an equation. We have to replace this by a concentrated load. But now we know how to replace this by a load. When we set with triangles, we just know very easily the area of the triangle. We don't need to do integrals here because everybody knows the area of the triangle. So what is the area of this triangle? 1/2 of 4 times 200, right? So, and that force will be going down, so will be negative, minus 1/2 of 4 meters times 200 newtons meters, right? That is the magnitude of this load that we are going to put it. Where do we put that load? Where do you think we should put that load?
1/3 of the direction.
Well, we are doing this kind of load. We are replacing that load. What we were replacing yesterday was something like this. Here is where it has the 1/3 thing here, right? 1/3 of B and 2/3 of B, where all this distance is B, right? That 1/3, 2/3 is for this kind of triangle, or do you want me to break this into two triangles, one like this and one like this? But this triangle looks even much easier than this one. Where would you put the resultant of this triangle?
No.
Huh? In the middle, because it's symmetric, right? In the middle. We can break this into two triangles like this and put one for the triangle on the left and one for the triangle on the right, and this will be 1/3 of 2, right? 2/3, and this will be 2/3. We can do that. We don't need it because this is so easy, symmetrical. It's better to put just one force in the middle. One force in the middle here will be much easier, right? And that force is this value here. Okay? Agree? Make sense? Misha? Brenda? Make sense? Santino? Everybody? Okay, let's continue. Is there any other force in the y direction?
There's the B going upwards.
The RB going up, so that's gonna be positive. I put negative this one because this one is going down. Positive RB plus RB. Do you have any more forces in the y direction? No, then equals to 0. Once you finish your summation, equals to 0. You have to put this equal to 0, don't forget it. Some people put just the summation and don't put the equals to 0. We know what you're doing, but you have to be correct in your math when you solve these problems. Next, and we can solve RB directly here, right? So therefore, RB equal to this minus something goes positive to the other side of the equation. So this is 400.
Yeah.
400 newtons. This meter goes with the meter, so 400 newtons. Okay, now summation of moments. Let's put it here. Summation of moments about. You can choose any point. We said we can do the equilibrium of moments with respect to any point, and it's going to be irrelevant. Any point works. So you choose the point that you like best. Remember that when a force goes through the point doesn't produce moment, right? So the trick to choose what point to use is the point that eliminates the larger number of forces. So I will choose this point here because I eliminate this force and I eliminate this force. So my equation is much simpler. Remember, I'm very lazy for algebra. So the simpler the equation, the better for me, less mistakes I make. So I'm gonna put summation moments about the center point of the beam. I am very smart. Center line equal to 0. I'm gonna put positive in this direction. Why? I usually do that. You can do whatever you want. I do this positive in the same direction of my unknown. So my unknown is positive in my left hand side of the equal sign. So for me it's much easier to solve the equation if I have a positive unknown here. Got the idea? Let me write it so you'll see. So okay, summation of moments about this point. M sub A positive. So, and I put here the underline. This is what I call the center line. Moment sub A. This force doesn't produce moment, right? Because goes through the point. This force doesn't produce moment, right? Because goes through the point. So only this one is left. So it will be RB times 2 meters, positive or negative?
Positive.
Positive, it's the same direction of this, right? So positive. So I'm gonna put plus RB times 2 meters. Any more forces that produce moment with respect to this point here in the middle? No more forces, right? I have the moment here. AX doesn't produce moment, will be AX times 0 to this force of this is 400, right? Right? This is 400. So that let me put that value here. Will be helpful to put in the 400 here. So the force of 400 concentrated here at this point doesn't produce moment. So only this one produces moment equal to RB times 2. RB times 2. So no more forces produce any moment equal to 0. So from here we can solve for MA, because then MA will be equal to minus RB. We already have it here, 400 times 2 meters. So MA will be equal to minus 400 is newtons, right? This is newtons. This 400 is newtons. Is 4 meters times 200 Newton meter. Meter with meter goes away. So this is 200 over 2 is 100 times 4 is 400. That's where this 400 comes from. So it's 400 newtons times meters. Newtons times meters. Newtons times 2 meters. So this is equal to minus 800 Newton meters. What does this mean?
Going downwards. It's opposite direction.
It means that this was not, I didn't assume the correct direction. It doesn't matter. It doesn't matter. It's just an assumption, and I didn't know what it was, so I put anything. So once you find that this is negative, you come here to your diagram. If you want, you can do this. Put like a X and draw it again on top, right? But don't erase it. Never erase this. Just leave it with a cross marking and then put it in the right direction. Because if you erase this, when somebody sees this equation, is going to say, no, this is wrong. Why? If it's assuming sign convention positive counterclockwise, and this is clockwise, so this should be negative here. Because if you erase this, the person is going to see this one, not this one, right? And remember, your work is always for someone else to check or to see it. So the moment at A, if you're gonna put the results of this problem, you will say something like, you can put here a note like this, indicating the direction that you just found out that the direction is opposite to what you assume initially. So put it like this. So the final result will be AX equals 0, RB equals 400. Important to put this, newtons, right? Newtons going up, and moment at A equals 800 newtons meters in this direction. You can put that, or you can put clockwise. Oops, I do want to erase my work. That will be the final solution. And that will be the end of the problem. Questions?
How come the answer is positive, not negative?
What?
So when we,
This?
yeah, when we did the math, it was negative, but then when we put the answer is positive.
Because this negative, the job of this negative is to tell you that you assume this wrong.
Oh, okay.
That's the only purpose. And now that you saw that this was wrong, you know that this is the right direction, right? So then this is what you have to put in here, the right direction. So now you know that this 800 Newton meter is clockwise. You can put this or you can put clockwise. And it's the same as this. I didn't do the whole about here we got a positive, right? We got a 400 newtons positive. What does this positive means?
There's a force of 400 newtons pointing going up.
It means that this assumption was correct. That's what this positive means. It's not that this is positive. This positive is not the same as this positive. This positive is telling you that this is going correctly. So that's why I put this arrow here, going up. Very important. Do not confuse your sign convention with the result here, because your sign convention is just for this equation. That's it, no more. The sign convention is very local, just for this. This sign convention is for this. This sign convention is just for this, until you get the sign to tell you, okay, it was correct, or it was in the opposite sense. Good. Another problem, a little more complicated. Are you ready for a more complicated problem? Another problem. Let's see what I have here. Let's see this problem. A little bit more complicated. Okay, determine the reactions at support A. So first, what is the first thing you have to do? A free body diagram. So since I want to find the reactions here, well, I'm going to remove this in order to see the forces. If I don't remove it, I won't see the forces. And once you do the free body diagram, you don't need to put here the dimensions of the beam, like the height of the beam is not really relevant for the problem, so you don't need to do it as.
This one doesn't have any like supports, right?
What?
This one doesn't have like any type of specific like connections.
Well, this one is in the table. Let me show. Good.
It's attached to the wall. Or it's similar.
It's over here somewhere. Can you see it?
Is it fixed support?
It's this kind of support.
Yeah, it's fixed. It's like concrete.
It's like attached to the wall with super glue. So let me draw the beam. I'm not gonna do it as thick. I isolate the beam from the rest of the wall. Basically, I erase the wall. So I can do the same analysis. Can I move it horizontally? No, because it's glued there, right? So there will be a horizontal force here. There will be an horizontal force here. You know, I'm gonna put it this way. I'm gonna put it this way. I don't care. I put it any way I want. This force, if I try to move this beam vertically at this point, can I move it vertically? No, it's anchored to the wall. So there will be a vertical force here. And can I rotate the beam here? No, there is no beam. That cannot rotate. If you try to rotate this, you break the wall and they will come and charge you, right? Or you can break it and you can tell the engineer that support was really weak. I'm not paying for that, right? So there will be a moment here, and actually I don't know the direction of that moment, so I'm gonna put any direction, whatever, like this. And I'm gonna put the forces, the rest of the forces. So I have a moment here of 200 Newton meter. Have a force here of 80 Newton per meter, and I have a force here of a 345 1000, where this is 345 1000 newtons, and I have some dimensions that I better put them there. So I have 2 meters. Oops. 2 meters, 1.5 meters, and 4 meters all the way there. I guess that's, well, I need to put some labels to the unknowns. I'm gonna call this one AY. I'm gonna put here AX, and I call this one MA. Now that's my free body diagram, beautiful. So Professor Salamanca is not gonna take 5 points off because my diagram is too little, too crooked. Beautiful, look, beautiful. Like it? Ranjit, you like it?
Better than what I made.
What?
It's better than the one I made.
Oh, I wanna see your diagrams. Are you doing nice diagrams?
Oh, yeah. Very nice.
Huh? What?
Very nice.
Very nice diagrams.
Try.
I did it wrong. This is up to here. See? This goes to the point of application of the load. I did it too long. Sorry. It'll be like this. So maybe I should draw this auxiliary line like this, see? Okay, so now we are at the point where we can do summation. We have the three unknowns. Summation of forces in the x direction. Summation of forces in the x direction equal to 0. I'm gonna do positive to the left because, as I said, I like to have my unknown with positive sign. So I will have AX. Any other force in the x direction?
3 plus times 1,000.
The 1000, the x component of the 1000, right? Let me put it better here. AX. So, and that one is positive also, right?
Yes.
So it will be 1000 times what?
Plus 1,000 times 3 over 5.
3 over 5. Everybody has clear why 3 over 5? Everybody is clear why 1000 3 over 5? Everybody? Everybody? Any other force in the x direction?
No.
I don't see, no? That component will be this one over here. I'm gonna put it, but usually we do this without really drawing it, right? So this one will be the famous 1000 3 over 5. And this one will be the 1000 4 over 5. Okay, so equals to 0. Equals to 0. So from here we can solve directly AX equals to minus, what is, this is to 600? 600? Minus 600 newtons. So as soon as you see the minus, what you do? As soon as you see the minus here, you see that, okay, this was not correct. So you can put a little note right here, this is to the right. You just put this arrow that comes from the fact that this is a negative, so that's telling you that this force is to the right, right? If you want, you can correct it here, but it's not really necessary. Nobody's gonna kill you. You can put like, no, it's not like this, it's like this. See? Okay? You can do something like this, but never erase the original. Never erase the original. Next, summation of forces in the y direction equal to 0. I'm gonna put positive going down because my unknown is going down, AY. So I have AY. Any other force in the vertical direction?
1,000.
The 1000. So and it's also positive because it's going down, right? So it will be 1000 times 4 over 5, right? Any other one?
The distributed load.
The distributed load, the 80, and it's gonna be 80 times 1.5, so there will be a force here in the middle, that on the middle, and the value of that force will be 80 times 1.5, right? So it will be 120, right? 120, so that force has to be also going down, so also positive plus 120, and I don't see any more forces, right? Moments don't get into summation of forces, so that's why this moment doesn't get into here or into here. So that's our whole set of forces in the vertical direction. So now we can close our equation with the equal to 0. Never forget the equal to 0. So from here, AY equals to minus, this is what?
920.
Oh, you go so fast. So it's 800 minus 120. So this is minus 920, you said?
Yeah.
As soon as you see the minus, you know that this was in the wrong direction, so you put a arrow going up here. This is very important here. Not as important as making a correction here, but this one. Next, the last one, so we can leave. 2 minutes for the last one.
Wait, what does that mean? Does the 920, there's force on the beam going up?
The wall is applying a force of 920 going up. This is the force that the
On
wall
the beam.
Applies on the beam. These are not the forces applied on the beam, all of them, including the forces that the wall applies on the beam.
I see. Okay.
And the force that the wall applies on the beam is going up. That's what this arrow means.
Wait, but isn't it negative, so it wouldn't be going down?
No, because I said the negative means
Opposite of what you.
opposite of this if you want, but don't think about that. Don't think about that. What I like to point out is that this negative means this assumption was incorrect. That's what it means. If you look at this, okay, yeah, this is positive going down, so that means negative means it's going up, right? But I don't like to make that point. I really want to make the point that as soon as you get an answer with a negative number, this was not correct, so this is going up. It's going to be the same concept, right?
Does that make sense logically though?
Right.
Because the arrow is pointing down and to the left.
This one?
Well, I mean, like the one on the arrow on the right, that's 1,000 newtons, isn't that based off of?
It's the force of the
the
wall.
wall's
The
resistance.
wall, the force of the wall.
Which
Running
one?
on the beam.
The
yeah.
1,000 newton load
Yeah,
on the beam,
that's the load on the wall.
on the,
Which one are you talking about?
he's talking
Never
about the
mind.
1,000 on the.
The 1,000 is going down, right?
Yeah.
So, and since it's going down, we put the positive sign here because we said, let's call positive everything going down. So that's why we put positive here. And then we solve the unknown, and the unknown gave us a negative sound. As soon as you see negative here, you see that this was incorrect, so you correct it. If you want, you can do this, but it's not necessary. You say, okay, this is not like this is actually like this.
Okay.
it's 1.
It just means at that point where you
But
make the
don't
assumption,
erase it.
force is going up instead of down.
Okay.
So shall we leave the other for the next class, or can you stay 1 more minute? 1 more minute, quickly. Summation of moments with respect to what point? Any point. Let's put summation of moments about point A equals to 0. I'm gonna do positive this direction. Okay? So this moment. I put it. Look. I put it positive going clockwise. So this one is negative, right? But I hate that. But I usually put the convention that positive in the same direction of my noun. But it doesn't matter. So that would be minus MA, right? Any other moment with respect to point A?
The 200.
The 200 newtons you have to put in, even though it's not here. I'm talking about moments about point A. You have to include all the moments in the beam. Because the moments move, imagine that this moment you can move it here. You can move moments anywhere you want. So that will be plus 200. And you don't need to apply any distance. That's why the problem didn't give us a distance, because no distance for the moments.
Well, it's already solved, right?
Yeah.
Like they already gave it to you.
This moment?
Yeah, it's a moment. Like,
It's a moment applied to the beams.
yeah.
That would be like maybe another beam that comes here with a torsion here. So that's a moment applied at that point. Next, the force of 120, and it's in the middle, right? So this distance is what?
3.75 from point A.
2 plus 0.75, so it will be 2.75, right? Okay, so 200. Okay, so that will be also positive, plus 120 times 2.75, that's Newton's meters, and then the 1000, also positive, the vertical one, right? The vertical component produces moment with respect to point A, is 1000 times 4 over 5, times 4 over 5, times the distance from here to here, 4 meters. 4 meters. And the horizontal component doesn't produce moment with respect to this point. So that's the end, equals to 0. So from here you get MA equals to, all this is positive. So can you do this operation for me? Nice.
1,730.
What is it?
3,730.
3,730.
730. 3730.
30, and I got positive, right?
Correct. Yeah.
We got positive because this, as you can imagine, this negative goes positive to this side, and everything is positive on this side, so it's positive. That means that this direction is correct. This direction is correct, so it's counterclockwise. So you can put it here like this. Okay? Good.
That's the distance from the concentrated load to point A.
Oh, we can already.
2 meters plus about half.
Let's already catch me by surprise.
Okay.
Oh,